Hello everyone. My name is Minh, and today the seminar topic that I present for today is also related to steel manufacturing. However, I consider a different process as well as a different kind of problem. The topic is scheduling and logistic optimization for batch manufacturing processes with temperature constraints and alternative thermal devices. Published in the Journal of IEEE Transactions on Industrial Informatics, published in 2024. The keywords are as follow: batch scheduling, green manufacturing, dual objective optimization, and logistic optimization. My presentation consists of the following parts. Steel manufacturing is one of the most important industry in which the main product are steel coils, which is widely used to several industries, such as the automobile manufacturing, civil construction, or shipbuilding industry. Steel coil manufacturing process involves several processing stages. In this study, we mainly focus on the hot rolling process. This is the illustration of the general workflow at the hot rolling process. The continuous casting stage is responsible for producing hot slab, which is a hard steel bar. They vary in sizes and can be used to manufacturing different types of products. The hot slab will be transported to the hot rolling process, but before input into the process, they will be assigned to a batch, and their processing sequence will depend on the position of the hot slab in the batch. The output of the hot rolling process is the finished product, which is the steel coil. The figure below illustrates the hot rolling process in detail. As you can see, the red bar in here is the hot slab. It must go through many rollers while it's still hot in order to form a desired form that can be rolled into a coin. Therefore, temperature is really important in the hot rolling process, especially in the manufacturing of high quality stainless steel. A temperature must be maintained within a fixed time period. Otherwise, it must be assigned to other thermal devices for additional heating ability. Speaking of the thermal devices, these are the thermal devices that usually used in the steel coil factory. There are two types of thermal devices. Their main function is to transport hot slab from the continuous casting to the hot rollings while maintaining a temperature. The first type of thermal device is the temperature holding hood, or TH. It can it does not consume energy. However, it can only maintain the temperature within a fixed period of time. The second thermal device is the soaking pit. It's like a chamber with a heating device installed inside. It can provide it can maintain the temperature as long as possible. However, it consumes the energy per time unit. The problem we consider is an integrated batching, scheduling, and logistic optimization problem. The first batching and scheduling problem can be formulated as follows. A job consists of many hot slabs with the same width or the same size. They will be arrived at different times. So we denote the job release time at RI. Job will be then assigned to different batches. And processed sequentially. Batches is processed sequentially. They set up time between two consecutive batches. We denote the job start time in each batch as TI, denotes for the job start time. So we denote the WI as the waiting time of a job. The waiting time of a job can be calculated based on the job start time and the job release time. The U in here is the time limit that a job can stay in the TH. Based on the time limit and the job start time, we can calculate the maximum waiting time of a job, which is T prime in here. In the first case, job waiting time is within the time limit, or in other words, job one start processing before the maximum job waiting time. Therefore, it does not require additional heat, and it can be assigned to the TH. However, in the second cases, the job waiting time exceeds the time limit, or in other words, the job starting time is after the maximum waiting time. Therefore, it requires additional heating, and it must be assigned to the SP and consume the energy. For the logistic optimization, we consider the root assignment. There are total 2 roots. Each root had different thermal devices. Root 1 had the TH. It can provide limited temperature maintenance, but it does not consume energy. However, in the root 2, it has the socket peak. It can provide the temperature maintenance time as long as possible with the cost of energy consumption. So the question is, why do we need to consider an integrated problem between batch scheduling and logistic optimization? The reason is that in the scheduling phase, the batching decision, the job start time, and the processing sequence of each job are highly affected by the duration of job staying in the TH or the SP for temperature maintaining. And the thermal device assignment or the root assignment is decided in the logistic optimization phase. In addition, these scheduling decisions will affect to the objective of the logistic optimization, which is the energy consumption. Therefore, we must combine the batching scheduling and the logistic optimization to fully address the concerned problem. The contributions for this study is as follows. First, we will propose an integrated production scheduling and logistic optimization problem. Then we will formulate a dual objective optimization, account for the temperature constraint and the energy consumption. And then we will design a meta-heuristic with a novel mechanism to enhance the algorithm performance. The problem we consider in here mostly relate to the hot rolling scheduling problem. These are the few characteristics of the process. First is serial batch manufacturing. It means that batch will be processed consecutively in contrast with the parallel batch manufacturing. And also, there is a consideration of the decoration of equipment. It means that the setup time will incur between 2 consecutive batches. There are 2 kinds of variant of batch scheduling problem. The first one is single batch scheduling problem. The decision variable mostly relates to job processing sequence within a batch, and it can be reduced to the travel assignment problem. Many research they consider 2-stage scheduling problem related to the soaking peaks and the hot rolling process. For the multiple batch scheduling problem, it involves more complex decision variable. First, we need to determine the number of batch required or the batching decision and the processing sequence of each batch, and the processing sequence of job within each batch is also need to be determined. There is many studies that consider 2-stage scheduling problem also from the soaking peak and the hot rolling process, or from the continuous casting and the hot rolling process. They also propose several methods, including the 2-stage method, using the exact method to solve the batching problem, and a heuristic to solve the scheduling problem. They also consider stochastic scheduling problem, which take into consideration the uncertain processing time. However, we found out that there is a research gap between the existing research in such that the hot rolling process, usually they did not consider the temperature constraint and also the thermal device assignment. And also, a lack of research, they consider an integrated problem of batch scheduling and logistic optimization at the same time. To describe the problem, Our problem is called the scheduling and logistic optimization problem with temperature constraint and alternative thermal devices, or SLTA. A job is consists of multiple hot slabs inside with the same width. In this case, we use another term, which is the rolling unit, to refer to a batch. A rolling unit will have a holding capacity and a rolling position. The holding capacity is the maximum number of slabs that can be contained in the rolling unit, and the rolling position is used to determine the job processing sequence inside the rolling unit. And the rolling replacement time or the setup time will occur between two consecutive rolling units. For the logistic optimization phase, we determine the route assignment, which consists of two routes. The first route has the TH, the temperature holding hood, and the second route has the soaking pitch. Each route has different thermal devices with different attributes to provide different temperature maintenance and heating options. These are the following assumptions for our model. First, there is no restriction on the number of jobs that can be assigned to each route. There are also no time limit for a job to remain on the soaking pit. The transferring time on both routes are ignored, and route in each rolling unit must be arranged in a non-ascending order of width. In other words, jobs in a rolling unit must be processed from the largest one to the smallest one. And finally, if a job is assigned to a route at the beginning, it cannot switch to the other during transportation. The first component for the dual objective optimization problem is the batch scheduling problem, in which the decision variable are mainly assigning job into the rolling position and determine the starting time. For the logistic optimization problem, we will assign route to job, or we call it thermal devices assignment. And then if a job is assigned to a soaking pit, we also need to determine the heating time of the job. The dual objective function consists of the primary and the secondary objective, in which the first one is minimize the number of rolling units or the number of batches, because the fewer number of batches, the lesser the total setup time, which allow more jobs to be executed. The secondary objective will minimize the energy consumption for thermal devices assignment. These are the notation for our MLP model. First is we define a set of job, a set of rolling unit, and a set of rolling position in each rolling unit. In this case, we make a general assumption that the number of jobs will be equal to the number of rolling unit equal to the number of rolling position in order to cover on the possible scenario. For example, if we consider a problem with 50 jobs, so we also will have 50 rolling unit in the case that we will assign each job to each rolling unit, and also we will have 50 rolling position in case that we assign 50 job into one rolling unit, and each job will be assigned to each rolling position. For the parameter, we will define first is the number of slab in a job, the width of slab, the processing time of job, the rolling unit capacity, the roller replacement time, setup time, and the maximum time a job can stay in the TH or the time limit. For the decision variable, xijk is the binary equal 1 if job I is assigned to the k position in the rolling unit j, and yi equal 1 if job j assigned to the soaking pit or the second route, equal 0 if job I is assigned to the th or route 1. And Ti is the start time of job I, Hi is the heating time of job I in the SP. It is assigned to the second route. The MLP model is follow. The first one is minimize the number of rolling unit. The second objective is to minimize energy assumption of a job, which is calculated based on the heating time multiplied with the number of slab in the job. For the setup constraint, constraint number 3, ensure that each job will be assigned to a rolling position in a rolling unit. Constraint number 4, a rolling unit can contain at most one job. Constraint number 5 is the assignment order of rolling position within a rolling unit. It means that the earlier rolling position must be assigned first and then come to the later one. Constraint number 6 is the assignment order of rolling unit. Similar to constraint number 5, if we have the earlier rolling unit, we need to assign to it first and then move to the second one and so on. Constraint number 7 is the processing sequence of job in the rolling position. Constraint number 8 is the processing sequence of rolling unit. Constraint number 9 is the capacity constraint of a rolling unit. The number of slab assigned to a rolling unit must be smaller than the rolling unit capacity. And constraint number 10, job must be processed in a non-ascending order of slab width. It means that job with larger slab must be prioritized to process before job with smaller slab. Constraint 11, ensure that the job start time is after the job release time. Constraint 12, job start time is influenced by the thermal device assignment. Constraint number 12, number 13, calculate the heating time of job in the S3. And the constraint 14 and 15 are decision variable constraint. In this study, we will use a framework which is built upon the simulated annealing algorithm, which is widely used to solve the travel segment problem. The SA consists of the main component, which is the initial temperature. The temperature in here is related to the probability of accepting new solution. At first, we will set the temperature high in order to extend the searching range for a potential solution, and the temperature will be decreased gradually using the cooling factor in later iteration. The objective function is the one that we want to optimize, in which the x is the solution. The local search operator, the SA rely on local search operator to generate new solution. I will introduce the local search operator in later part. The acceptance criterion is the probability function, which take the objective value of the current solution and the new solution and the temperature in order to calculate the probability to accept new solution. By using the acceptance criterion, SA can accept worse solution than the current one in order to find more potential solution. The SA solving procedure is quite straightforward. We randomly generate new solution using the local search operator. Then we evaluate the quality of the new solution and decide whether to accept or reject it. And then we will repeat the procedure until we reach a stopping condition, usually when the temperature reach a limit. You can see in this illustration, this illustration is the SA solving procedure. As we can see that there is many local optimal exist with one global optimum. And you can see that when temperature drop, the algorithm mainly focus on the global optimal and avoid other local one. For the framework that we propose is called the SADC framework. We introduce a destruction and construction or DC mechanism to escape from the local optimum. It is the ability to modify the solution into the new one, which can help us, which can allow the algorithm to escape from local optimum. We also enhance the algorithm exploratory ability by using various local search operator. And also, because we consider a dual objective function, we also need to design a new acceptance criterion to adapt to it. The pseudocode for the SADC framework mainly consists of 4 parts. First is the initialize solution, generate new solution, evaluate it, and then apply the DC mechanism to it I will explain one by one. The first one, we initialize the solution pi, and then we will set it to be the current best solution pi star. Then we generate new solution using the local search operator. In this step, if the current solution is better than the current best one, then we also accept it as the current best solution. And then we evaluate the new solution using the acceptance criterion, which is the comparison between the new solution, the current solution, and also the temperature. So we will obtain the current solution pi in here. It means that in this state, pi prime will be pi, or pi will be the same, will remain the same. And finally, after obtain pi in this state, we apply the DC, destruction construction, to obtain the new solution and compare with the current best solution to obtain the final pi star. When using meta-heuristic, it's really important to do the encoding and decoding to adjust the problem to the algorithm solving procedure. In the encoding part, we have a solution pi. The solution is represented in pi, and pi q refer to the job in the q position. So the q can take any value from 1 to the number of I. So the solution can be like this one, where different batch are grouped into together. And for example, pi 1 will equal to job 1, pi 2 will equal to job 2, pi 3 will equal to job 5. And the processing sequence of each batch can be considered in the solution, in which the processing sequence of batch 1 will be from job 1, then job 2, and job 5. Processing sequence of batch 2 is from job 4, then job 3, and finally job 6. Based on the encoded solution, we can obtain the job release time and job processing time. For the model decoding, first, based on the solution, we will calculate the job start time. If it is the first job Q equal 1, then the job start time will be equal to its release time. If the job is on different batches, for example, job 5 and job 4, then job start time will be equal to the maximum of job release time and the completion time of the previous job plus the setup time. If job on the same batch, for example, job 2 and job 5, then the job start time will equal to the maximum release time and the completion time of a previous job. Then we will calculate the heating time. The heating time in order to determine the thermal devices assignment. If the waiting time is greater than the time limit, then it must be assigned to a socket pit SP, and the heating time will equal to the waiting time. Otherwise, it can be assigned to the TH, and the heating time equals 0. Based on the start time and heating time, we can calculate the primary and secondary objective value, in which, in this example, we have two rolling units. So the first objective value equal 2, F1 equal 2. For the second dairy objective, in here we assume that job 1, 2, 5, and 6 will be assigned to root 1, which is TH and does not consume energy. But job 3 and 4 will be assigned to root 2 and consume the energy. So the secondary objective will be calculated based on job 3 and job 4. Finally, we combine the two objectives into one big F function. For the initialization state, first we will sort the list of jobs according to the descending order of release time. Similar to FIFO, the job arrive early will be processed first, and then we will assign job into batches and must satisfy the backside the width constraint as explained in the MLP model. In this example, assume that we have 4 jobs from job 1 to job 4 that has been sorted in the descending order of release time. Job 1 arrive first, so we can assign job 1 into rolling unit 1 at rolling position 1. Job 3 assign later than job 1 arrive later. However, it cannot be assigned to the rolling position 2 at rolling unit 1 because the maximum backside is 5 slab, but the total number of slab in job 1 and job 3 is 6 slab, which is exceed the backside, so we need to assign job 3 into the second rolling unit. Assume that job 4 will be later on assigned to rolling unit 2. Therefore, job 3 must be processed after job 4 due to the width constraint. Job with larger slab will be processed first, and then finally we'll assign job 2 into the rolling unit 1 at the remaining rolling position, and then satisfy the backside constraint. For the local sort operator, it consists of 4 operators to generate new solution. For each iteration, we will randomly choose an operator to produce a new solution. The operator will be denoted from L1 to L4. The first L1 is inner insertion. We randomly insert a job to another position inside the batch. The second L2 in a swap, we randomly swap position of job inside the batch. The inter-insertion, we randomly insert a job position to another position outside of the batch. The inter-swap, we randomly swap position of jobs outside of the batch. The solution from the local sort must also satisfy the constraint, the backside, the width constraint. And because during the local search operation, infeasible solution may occur, therefore we must set some rule to prohibited action that lead to infeasible solution, and this also accelerate the searching time. The acceptance criterion we consider is the MAC. It is the probability to accept a new solution. This allowed our SADC framework to accept even worse solution within a certain probability. Let's consider first case, if the new solution pi prime is strictly smaller than the current solution, then we accept the new solution without any doubt. However, otherwise, we will accept the new solution if it satisfies the 2 following conditions. The first one is the primary objective value are the same. The second one is that the probability calculated based on this formula is smaller than a predefined p-value. For the destruction and construction mechanism, it is the ability to modify the solution into the new one. The procedure is as follows. First, we will search for the batch that consumes most energy in the solution set, and then we will call it the remove batch or pi r. The remaining batches will form a partial solution set or pi d. We will insert each element in the pi r into its best solution in pi d. This mechanism can potentially decrease the number of rolling units, which is our primary objective. So how do we check if it is the best solution? Let's have a look at this example. For example, we consider pi r consists of the following job, and pi d consists of the following job. We will insert each job in pi r into pi d. The first job is job number 4. So after insert, the pi d will, the job 4 will be inserted in this position in the pi d. And then we will compare between the new solution and the new solution with the best solution and obtain the current solution. We repeat until there is no job left in the remove batch, and we obtain the new solution. For the experiment, first the experiment testing as follow. We will test on different number of jobs from 10, 20, 30, 40, and 50. The number of slabs will be vary from 5 to 30. The backside is assumed to be 200 slabs. Roller replacement time is assumed to be 20 minutes. The time limit in the TH is 300 minutes. For the parameter for the meta heuristic, the first we consider different initial temperature and then different cooling coefficient and also different number of outer and inner loop iteration. For other method, for other comparative pairs, we'll compare with exact method. We limit the solving time to 1 hour and compare to other meta-heuristic method, which is suggested in other study. I put it in the appendix. For the evaluation matrix, we will evaluate based on the following matrix. The first is ranking. So for each instance, for each data set, we will test on 5 instances and we will rank each solution. The solution will be ranked first. From the smaller F1 will rank higher. And if two solutions have the same F1, then we'll continue to rank based on the F2 value. And then we evaluate on the average primary objective value, the number of rolling units. And then we will see the number of times we obtain a minimum primary value. We denote it as C F prime F star 1. And then we consider the average secondary objective value, the amount of energy consumption, and energy saving effect E, which is the solution gap between SADC with other method, calculated based on this formula. For the sensitivity analysis, we will use grid search for parameter tuning using a large size dataset, 50 jobs. Experiment will be conducted on 5 instances. Each will be tested for 10 times. So we assume that SADC under different parameter configuration always obtain the same F1 value. While the proposed algorithm can show consistency toward the primary objective. However, the F2 value vary significantly across different parameters. Therefore, after fine-tuning, we obtain the best configuration, which is the red dot in this figure. For the computational result, we will run each algorithm 10 times for an instant and obtain the average result. The first table is the comparison of the ranking. So we can see that the SADC, it achieved the highest rank for 19 out of 25 instances. The performance of the exact method downgrade at the medium-sized problem, 30 jobs, and it cannot solve for larger instance within 1 hour. And we also assume that observe that other method performance decreases as the problem size increases. To further investigate the accuracy and consistency of the algorithm, we will divide the rank into 5 ranges for comparison. For example, as you can see at instant 51, the ANSA 1/3 of the solution, it ranked between 0 to 20%, 1/3 of it from 20 to 40, and the rest on 40 to 60%. So we observe that all the solutions of SADC are all ranked in the top 20% in all testing instances, which outperform other competitors. Then we compare the average primary and secondary objective value, the energy saving effect of SADC versus other one, and see that SADC can achieve minimum F1 for all the instances, and with the number of time it achieved the minimum F1 is 10 out of 10, while different F2 value also lead to the deviation of ranking in the table 1. We also observe that other method can hardly achieve minimum F1 value, especially for larger size, as we can observe that the C value decrease in the when the problem size increases. And we also observe that SADC is more energy efficient than other method, effectively can handle a multi-objective SLTA problem. So we also investigate the performance of SADC under the removal of different components. When we remove some component, we will denote it behind the minus sign here. For example, SADC minus DC is mean that we will remove the DC mechanism into the framework. We will test on different components. We will remove each local sort operator, or we remove the DC mechanism, or we remove the acceptance criterion, and then compare with the baseline algorithm. It shows that any removal of any component may result in poorer performance, which emphasize the importance of each one of them. Among them, when we remove the DC mechanism, it shows unstable F1 value when solving loss size instances. And you can see that in other instances, it achieves minimum F1 value 10 out of 10 instances, but as the problem size increase, it can only achieve the minimum F1 value for 6 or 9 or 4. So we conclude that SADC without the DC mechanism is easily to get trapped in local optima, thus indicate the importance of the mechanism into solving the SLTA problem. For the conclusion, in this study, we address a complex dual objective hot rolling scheduling and logistic optimization. We also formulate and propose an MIP model for the concerned problem. And then we develop the conventional SA with the DC to improve the performance. We also conduct extensive experiment to compare between the proposed algorithm versus other. And then we conclude that the framework not only effectively handle the primary, but also the secondary objective. For the future work, we will consider uncertain factor in production condition and market demand, and also develop the robust or fuzzy optimization techniques to tackle the uncertain factor. This is my opinion. For the strain, this study, they consider an integrated problem of scheduling and logistic optimization. They also design different parameter performance matrix to measure the dual objective solution. And they also validate their proposed mechanism through various experiments. For the weakness, I think that it needs to consider the capacity on both two root to reflect the real-life cases. And also different value of other parameter also need to be covered for a wider range of production scenario. And also this is not a significant weakness, but I think that for those who are interested in the topic, you may not get confused because they will have some incorrect notation in the MLP model and the SADC algorithm, which I will show in the appendix. For example, in the MLP model, it should be exclude the final rolling position and exclude the final rolling unit instead of exclude the total set as denoted in here. And for the SA and DC initialization phase, the backside constraint and the width constraint are not constraint 7 and constraint 11. It should be constraint 9 and constraint 10. These are the list of meta heuristic used for comparison. This is the end of my presentation. Thank you for your listening.